Bismillahirrahmanirrahim. Let's start single phase induction motors. So the construction of a single phase induction motor is shown. The rotor construction is same as that we have already discussed in cage type three phase induction motors. So normally for single phase induction motors the cage type rotors are used. The stator construction has already been discussed in the first chapter related to AC machines, where we discussed the fundamentals and we also discussed the type of magnetic field that is produced by a single phase supply. Just remember or recall that lecture where we discussed that a single phase supply produces a bidirectional pulsating magnetic field which is not rotating. For producing rotating magnetic field, the polyphase supply is necessary. It means that for two phase or three phase supplies, we will have revolving magnetic fields. However, for a single phase supply, we will have a pulsating bidirectional magnetic field. And to apply a single phase supply, or in other words, for a single phase two pole armature, we require minimum of two slots for the simplest of the armature windings, which will consist of only one coil. So let's assume that we have a single phase motor and a single phase supply is provided to a two pole armature. You can see that it is a two pole armature winding. The motor will not start. Why the motor will not start? Because there is no revolving magnetic field. As there is no relative motion, since the revolving field is absent here, so there is no relative motion between the rotor and between the stator magnetic field. So there is no relative motion between the stator magnetic field, which is shown by this red arrow and is pointing upwards at this instant for the current entering in this conductor and the leaving through this conductor. The stator magnetic field is pointing upwards. This field is not rotating. This is just a bidirectional field. In the positive cycle, it is pointing upwards. Then in the negative cycle, the current flow will reverse cross in this conductor and out of the paper dot in this conductor. So the current direction, so the stator field will point downwards in the negative cycle. So it is not a rotating magnetic field. Since there is no relative motion between the conductors and the field, so no voltage will induce in these conductors or in this coil CD. However, a voltage will still induce in the coil AB. It is because of the transformer action. Since an AC supply has been provided, so it means that the voltage is changing with respect to time. So does the current will also change with respect to time, and the current will produce a flux or the stator field, which is also a time changing flux. d phi by dt is non-zero. So if d phi by dt is present, the rate of time change, the time changing flux is there. It will cause a voltage to induce in the coil AB just on the same principle as the voltage is induced in the secondary winding of a transformer. So the coil AB in this case is just behaving like a short circuited secondary winding of a transformer. So according to Lenz's law, this statically induced EMF in coil AB will oppose its cause. The cause is the flux stator magnetic field, which is pointing upwards. So how can we determine the direction? The flux produced by the current flow in coil A, B will oppose the causing flux which is pointing upwards. It means that the flux due to current in coil A, B will point downwards according to Lenz's law. It should oppose its cause. So using right hand rule, we can mark the polarity in the conductors. It is cross into this conductor and it is dot in this conductor. So the curling of the fingers will show the direction of current into the paper in conductor A, out of the paper at conductor B, and the thumb points downward. This is the flux which is produced because of the statically induced EMF in coil AB. We discussed earlier that for torque production, there are some conditions that can be mentioned in alternate ways. So one of the conditions for torque production we can discuss here, that we should have a conductor carrying current placed in a magnetic field. Here we have zero current. The conductor is there, but the current is zero. How much torque will be produced? Zero. No torque will be produced. We have another set of conductors A, B, which are carrying current. However, you can see that they are placed outside the magnetic field. So conductor carrying current, but it is not placed in the magnetic field. So no force will act on these conductors. Alternately, we also discussed in case of in case of induction motor torque production, that the conditions for torque production can be written in this form. There should be two fields. Here there are two fields. One is pointing upwards, BS, and the other one is also present, which is BR. However, it is pointing downwards. So no torque is produced according to our previous discussion. Similarly, we can write it in this way. The relation has already been discussed in the three-phase induction motor torque production case. BS BR sine of delta into some constant. Now here delta is 180, torque is 0. Also, if the delta is 0, again sine of 0 will be 0, so torque will be 0. Then what is the condition when the torque will produce? Just see here, if we have conductors carrying current placed in magnetic field, torque will be produced. In this particular condition, when the cross is here, the dot is here, the field due to current in this coil will point leftwards, and we have two fields. One is BS, which is pointing upwards, the other field which is pointing leftwards, BS BR into sine of delta. Here delta is 90 approximately, so the torque is maximum. Alternately, we can also mention this condition in this way. Magnetic field BS is due to flux phi s. Similarly, the field BR is due to flux phi r, and ultimately this flux phi s is due to current IS, and this flux phi r is due to current IR. So we can directly write the torque equation in this way, in the form of currents as well. So we can discuss the two ways of producing torque. Alternately, that conductor carrying current placed in a magnetic field, the torque will produce. Or alternately, there should be two fields that are at an angle of other than 0 and 180. The angle between the two fields should be other than 0 and 180, then torque will be produced. Now, if the rotor is rotated by some external means, let's assume that we have rotated the rotor by hand or by some external means, the rotation is produced in counterclockwise direction, then it will keep on rotating. Now, why it will keep on rotating when the rotor is rotated by externally in any of the directions? Here we have assumed that the direction is counterclockwise. See what happens. BS still pointing upwards. We have taken the same instant of time. Current is entering here, leaving here. So the stator field is still pointing upwards. Now we have rotated the rotor in counterclockwise direction. It means that this conductor C, which was under this magnetic field, now rotating in counterclockwise direction, it has some relative motion, or there is some relative motion between the conductor C and the field BS. With the help of right hand rule, we can see that the first finger points in the upward direction, that is the direction of BS, and the direction of rotation is shown by the thumb, which is counterclockwise here. Then the second finger will point in the direction of voltage induced, and if the circuit is closed, the direction of current flow, which is into the paper. So it means that the voltage will now induce in the coil CD. This is because of the rotation. This is known as rotating EMF because it is produced because of the rotation. It was not produced earlier when the rotor was stationary. At that time, the only EMF produced was in the coil AB, and it was the statically induced EMF. The EMF induced in coil CD is because of rotation, so it is sometimes also known as rotating EMF. Now what actually happens? We can see here that this condition has been attained, that Vs is equal to Dr. We can see that the conditions for torque production have been fulfilled. Vs, Dr, and the angle between them is other than 0 or 180, so torque will be produced. So let's see what actually happens in the motor when the motor rotor is rotated by some external means. Let's first of all draw Bs. Since we have a single phase AC supply, it produces sinusoidal, or it causes a sinusoidal current to flow in the armature winding. It will produce a sinusoidal flux or sinusoidal magnetic field Bs. The magnitude of the field will vary as the current will vary. So we can draw a sinusoidal field Bs, which is represented here. The strength of the field will vary as the current flowing in the armature winding will change. The current is maximum, flux will be maximum. The current is 0, flux will be 0. When the current will be negative, the flux will also change its direction, and we can have this sinusoidal flux wave here, Bs. Now when the rotor is rotated externally, the conductors cut flux. Voltage will be induced, the circuit is closed, current will flow, which will produce magnetic field Dr as is shown in the previous figure. Now from the previous figure we can also see that Dr is at an angle of 90 degrees with Vs at the instant which has been shown here. So it means that Bs and Dr will be at an angle of 90 degrees to each other. So if this is Bs, we can draw Dr, because the supply produced to the motor is a single phase AC supply. It means definitely Bs is sinusoidal, Dr will also be sinusoidal. And it is at an angle of 90 degrees with Bs. So we can draw Dr. Again, it will be sinusoidal. So at 0 degrees, just see at 0 degrees, Dr is 0 and the only field present is Vs. So net field present in the machine armature is Vs at 0 degrees. At 45 degrees, both are non-zero and are positive. And since Bs and Dr are at an angle of 90 degrees to each other, if this is Bs, then Dr is at an angle of 90 degrees to Bs. So net field will be the phasor sum of these two, Bs and Dr. It is pointing in this particular direction. At 90 degrees, Bs is 0. The only field present in the rotor or in the machine, the only field present in the machine is Dr, which is still positive. So it is shown here, the net field present in the machine is now equal to Dr at 90 degrees. So just move forward at an angle of 135 degrees. At an angle of 135 degrees, Dr is still positive, so it will be drawn in the same direction. However, the direction of Bs has been reversed. So it will be drawn in the opposite direction now. Previously it was pointing upwards, now it will point downward. However, Dr will point in the same direction as it is still positive. The net field is again the phasor sum of these two. So it is pointing in this direction. At an angle of 180 degrees. So at 180 degrees, this is 180 degrees, you can see that Dr is 0 and Bs is still negative. So the only field or the net field present in the machine is pointing downwards and is equal to Bs at 180 degrees. At 225 degrees, we can see that Bs is still negative and the Dr is also now negative. It has also changed its direction. So we have drawn Dr in the direction opposite to that of the positive direction, and the net field present in the machine is again the phasor sum of these two. At 270 degrees, we can see at 270 degrees that the field Dr is now 0 and the only Bs is 0 and the only field present in the machine is now equal to Dr. So the net field points in this particular direction. So what actually happens, the rotation of the rotor by external means actually produces a revolving field in the machine. You can see that net field in the machine is now revolving, pointing upwards, pointing at certain angle, pointing leftwards, pointing at a certain angle, pointing downwards. So the field B net, C B net, the net field present in the machine is revolving. So the rotation by hand produces a revolving field in the armature. Now if the revolving field is present in the armature in the direction of original spin, in the field will be produced, the revolving field will be produced in the direction of the original spin. The rotating flux will accelerate the rotor to near the synchronous speed. Since the two fields BS and BER make a cross to each other, this theory is also known as a cross field theory. Here, since they are making a cross to each other, this theory is known as a cross field theory. This theory is used to explain the rotation of the rotor once it is rotated by hand. The other theory that can be used to explain the behavior of a single phase induction motor when it is rotated by some external means, why it keeps on rotating, it is termed as a double revolving field theory. One of the theories has been discussed, it is the cross field theory. The other theory that explains this rotation of the motor once it is rotated by some external means is the double revolving field theory. Just see that single phase supply has been provided to the armature, so it will cause a single phase current to flow in the armature winding. The current can be represented as I is Im cos of omega t. We can write it as a function of sin omega t or as a function of cos omega t. Here we have mentioned it as a function of cos omega t for our easiness. Now if the current is sinusoidal, it will produce a flux. The flux will also be sinusoidal, phi m cos of omega t. So flux is a function of time here. With respect to time, the value of flux is changing. Now just see, we have a two-pole machine. The field is pointing rightwards, the pole is north, this one is the south pole. And let's assume that we have placed a conductor here at this point, or some just we want to see the magnitude of flux at this point with the help of a conductor here. Here at this point, let's assume that the angle, the reference angle is 0. We are starting from this point, the reference angle is 0 and the flux is maximum. The conductor is linking with maximum flux, it is cutting maximum flux. Now suppose the conductor is rotated in counterclockwise direction, and this particular, at this stage the angle is theta, at this stage, at the second stage the angle is theta. Now the conductor is lying outside the magnetic field, the flux linkage is 0, it is crossing now 0 flux. The conductor is further rotated in the counterclockwise direction and we come to stage 3. Here the conductor has been rotated by an angle of 180 degrees and now it is crossing again the maximum flux, but now in opposite direction. The flux is now linking with it in opposite direction, or in other words you can say that the flux is minus maximum here. The conductor is further rotated at 270 degrees, again it is crossing 0 flux. So it means that flux is also a function of space. Flux is a function of space here. At 0 degrees maximum, 90 degrees 0, 180 degrees minus maximum, 270 degrees 0. So this behavior is basically representing a cos function. Cos of 0 maximum, cos 90 0, cos 180 minus maximum, cos 270 0. So we can write the equation in this form: phi is equal to phi m cos omega t cos of theta. Just multiply and divide with 2 on the right hand side of the equation. So we can have phi m by 2 into cos 2 cos omega t into cos of theta, and we can remember or apply this trigonometric identity that 2 cos a cos b is cos a plus b plus cos a minus b. With the help of this trigonometric identity, we can write cos omega t plus theta and cos omega t minus theta. We can write it as phi m, the flux, cos of omega t plus theta, and phi m cos of omega t minus theta. Now what this shows? This shows that we have two revolving fields, or we have decomposed a single field, a single bidirectional magnetic field, bidirectional stator field, into two revolving fields that are revolving in opposite direction, as is shown by this angle theta value, or plus theta minus theta. One of the field is rotating in the direction of increase in the value of theta, the other one is progressing or is revolving in the direction of minus theta, or the angle is changing in the negative direction, and it is shown here phi m cos omega t plus theta, and this one is increasing in the negative direction, and at any time the net field is the phasor sum of these two stator fields that are revolving in opposite direction, as is shown here. When both of these will lie in this particular direction, the field will be maximum, as is shown in this case. The field will be maximum. They are now pointing at certain angles. The phasor sum will give us the net field, the net stator field, which is actually bidirectional and is just varying in magnitude in the positive and negative directions. When these two are at an angle of 180 degrees to each other, the net field will be 0, as is shown. At this point, the net field will become 0. Then it will become, again, the field will start increasing in the opposite direction, and when both of these phasors, this one and this one, the one which is revolving in counterclockwise direction and the other which is revolving in clockwise direction, both will point in the leftwards direction, again the field will be minus maximum, as is shown here. The field will be minus maximum here. So a single bidirectional varying magnitude stator magnetic field has been decomposed into two revolving fields that are revolving in opposite directions. One is revolving in clockwise direction, the other one is revolving in counterclockwise direction. Let's assume that the one which is revolving in the counterclockwise direction is taken as the forward field, and the one which is revolving in the clockwise direction is termed as the backward rotating field. Now each of the two revolving fields will produce a torque, just like the torque which was produced in the case of three-phase induction motor. In case of induction motor, just remember, three-phase induction motor, the torque speed curve can be drawn in this form: the motoring region, the plugging region. Here the forward field will produce forward torque, the backward field will produce a backward torque, and it is shown here. Just like the case of three-phase induction motor torque speed characteristics, the revolving fields will produce torque speed or torque in case of induction motor. The forward field producing forward torque, and the curve is shown in this form. The backward field is producing backward torque, and the torque speed curve is shown in this form. The net torque will be the sum of these two, Tf and Tb, or the difference of these two, Tf minus Tb. So you can see here that this one is positive, this one is negative, both have same magnitude at start when speed is 0. Speed is 0 at this point, so net torque is 0. Net torque is Tf minus Tb, net torque is 0. As we move in the forward direction, the magnitude of Tf is increasing and that of Tb is decreasing, so there is some non-zero value of the torque at this side. And similarly, if we move in the backward direction, if we rotate the rotor in the backward direction, then Tb will be larger than Tf, so the field will point in this direction, or the net torque will be now in the backward direction. So the net torque is shown by this dotted curve, and you can see that at start the net torque is 0. So at start the net torque is 0. It means that the starting torque of a single phase induction motor is 0. That is why the motor will not start when we switch on the supply, and when we put some when we rotate the rotor mechanically or by some external means or just by hand, then the motor will keep on rotating in that particular direction. The reason is that once the rotor speed is non-zero in any particular direction, suppose in the forward direction, Tf will become larger than Tb, so the motor will keep on rotating in that particular direction. The net torque curve is again shown here. In the forward direction, you can see that Tf is greater than Td, so net torque will be 0. The motor will keep on rotating in this direction. Since this theory assumes that there are two revolving fields produced by a single phase supply, it is also termed as a double revolving field theory. With the help of this theory, we can also solve the equivalent circuit for a single phase induction motor. Just assume that we have a single phase induction motor. The supply is provided to the armature at standstill condition. Both the torques are equal, so net torque is 0. The forward field is making to rotate the forward field is rotating in the counterclockwise direction and is shown here. Definitely it will be rotating at the synchronous speed as is shown NSF. Similarly, the backward field is also rotating at the same speed, however in the opposite direction, in the clockwise direction, and the field is shown by, or the speed of the field is shown by NSD. The backward field rotating at synchronous speed in the clockwise direction. This is producing a forward torque, this is producing the backward torque. This is the condition at standstill when NR is 0. The equivalent circuit of single phase induction motor is similar to the per phase equivalent circuit of three phase induction motor. Just recall the equivalent circuit of three phase induction motor. At standstill, NR is 0. Now we will redraw this equivalent circuit keeping in view the forward and backward torques that are produced in the rotor of a single phase induction motor and standstill condition. So just see, we have just used the single phase equivalent, the per phase equivalent circuit of a three phase induction motor. You can recall this equivalent circuit back in the three phase induction motor lectures. So we have just used that circuit and we have divided this circuit into two parts. Each value on the rotor side or on the magnetizing branch is divided to half. This one refers to the forward field and forward torque. This one refers to the backward field and backward torque. Since at standstill condition Tf is equal to Td, so it means that the circuits at standstill condition will be exactly equal or exactly same. So both the field or both the rotor circuits will produce equal but opposite torques, so the motor will remain in standstill condition. Now suppose that the rotor is rotated by some means in the forward direction. The motor will start revolving in the forward direction at a speed of Nr. You can also rotate the rotor in the backward direction as well. However, we will assume that here we have rotated the rotor in the forward direction. So the forward slip can be calculated as Ns minus Nr by Ns, or we can write it in this way, 1 minus Nr by Ns. It is termed as Sf, the forward slip. The backward slip can be calculated as Ns plus Nr. You can see that NSF is equal to NSD, the values are same. However, the direction of rotation is opposite. So here in the forward direction, the rotor is chasing or it is rotating in the same direction as that of NSF. So we have a negative sign. Here both are rotating in opposite direction. You can see here NR is rotating in the counterclockwise direction and the field in the backward direction is in the clockwise direction. So the relative motion will be the sum of these two, Ns plus Nr. Or we can alternately write it as 1 plus Nr by Ns. It is the backward slip. Just adding the equation 1 and 2, we can have this relation 2 is equal to Sp plus Sf, or we can write the backward slip in terms of the forward slip as Sb is equal to 2 minus Sf. Therefore, the equivalent circuit of single phase induction motor in running condition will be marked as R2 by S, the forward slip, R2 by SD, the backward slip. At standstill condition, the circuit will look like this, which was decomposed to this form, and in the running condition, we have decomposed the circuit with the help of the slip values SF and SB. Now let's simplify this circuit. We will resolve this circuit. The series combination of these two, the rotor side impedances, the series combination of these two is in parallel with the magnetizing branch. Similarly, these two, the series combination of these two is parallel with this branch. So we can write it as, the simplified form is written as RF, the forward side equivalent resistance, JXF, the forward side equivalent reactance, the backward side equivalent resistance, and the backward side equivalent reactance. And the current I1, the current drawn by the motor can be calculated as V, the applied voltage, divided by the total impedance, this total impedance. Now forward side impedance can be mentioned as, the backward side impedance can be mentioned as. You can see that for simplification we have ignored 0.5 factor. It can be ignored, it can be included by just multiplying ZF, the calculated value of ZF, with 0.5. Instead of multiplying 0.5 with each of these values, we have first of all calculated ZF using the equivalent circuit values R2, X2, Xm. Similarly, ZB has been calculated, and then after calculation, ZF is multiplied with point F to calculate these values. Similarly, ZB is multiplied with 0.5, sorry, half, to calculate these values. Power flow in a single phase induction motor. The input power will be given as P in is VI 1 cos of phi. From the input power, the copper loss from taking place in the stator winding will be subtracted. The first loss that will take place after the supply is connected to the motor is the stator copper loss that will occur because of the current flowing in the stator winding or in the armature winding. This loss can be calculated as I1 square R1, where R1 is the resistance of the armature winding or the stator winding. The remaining power will cross the air gap and it will enter into the rotor circuit. This power is known as the air gap power, as we already know from the three-phase induction motor discussion. So it is calculated as P in the input power minus the stator copper loss. It is the air gap power that is crossing the air gap and is entering into the rotor. So this is the input power to the rotor. Now in the rotor circuit, this air gap power is distributed in across two resistances. You can see that there are two resistances as compared to the case of a three-phase induction motor, where we will have a single resistance value. Here we have two resistances. One is 0.5 RF, the other is 0.5 RB. So the air gap power is distributed across this resistance and across this resistance. So we can calculate the air gap forward power. The air gap power which will tend to produce the forward rotation. It is I1 square 0.5 RF. This will tend to produce the forward torque. The other one is PAGB, the air gap power, which will tend to produce the backward torque, I1 square 0.5 RB. Since the motor is now in the running condition and it is assumed to be rotated in the forward direction, so it means that TF is larger than TB. So net torque is TF minus TB. So we can calculate the net air gap power. Since this is producing forward torque, this is tending to rotate the rotor in the opposite direction. So the net air gap power can be calculated as PAGF minus PAGB. This air gap power will also cause current flow in the rotor circuit and it will produce rotor copper loss as well, that we will discuss afterwards. Now the forward torque can be individually calculated as well. Forward power divided by omega s, just like the case of three-phase motor, the air gap power divided by omega s will give us the induced torque. Similarly, the backward air gap power divided by omega s will give us the backward torque. The net induced torque is the difference of these two. Or alternately, we can use this net air gap power, net PAG, divided by omega s will give us the net induced torque in the machine. From the three-phase induction motor equivalent circuit, we also know that if slip is multiplied with the air gap power, we get the rotor copper loss. Just recall the discussion for the three-phase induction motor case. We are familiar with this relation I2 square R2 by S. SPG is the rotor copper loss. In the same way, the rotor copper loss for single-phase induction motor can be calculated. Forward rotor copper loss, the power the air gap power in the forward direction, that will tend to produce the forward torque multiplied with the forward slip. Similarly, the backward rotor copper loss, the air gap power which will tend to produce the backward torque multiplied with the backward slip. So we can calculate the total rotor copper loss in this way: SPG, SPG in the forward direction, in the backward direction. Now, the air gap power, the total air gap power which is calculated here, PAG, PAG minus the rotor copper loss that we have calculated here will give us the converted power. We are familiar with these relations from the three-phase induction motor case. P converted minus P rotational will give us P out. If output power is known divided by omega m, we can calculate the output torque, the torque which is available at the rotor shaft. Alternately, we can also calculate the converted power in another way. P converted is omega m into induced torque. Omega m can be written in this form: 1 minus omega s. Now the induced torque can be written in this form: net PAG divided by omega s. So T induced has been replaced by net PAG divided by omega s. So we can solve it to obtain this relation, that converted power is equal to 1 minus S. Here the slip is the forward slip. SF, F is not written here, so we can add it at this stage. F, the forward slip, into the net PAG. Net PAG, that is this one, PAGF minus PAGB. So we can calculate the converted power in alternate ways. One is to use the total PAG minus subtracting the total rotor copper loss. The other way is to use this relation: 1 minus the forward slip into net PAG, and the rest remains the same. The rotational losses will take place in the single phase induction motor, just like the case of three-phase induction motor. So the output torque has been calculated. The power flow diagram can be used to express these stages as is shown here. The input power, first of all, the stator copper loss is subtracted. The remaining power will transfer across the air gap to the rotor. Here the rotor copper loss will be subtracted from this power. The remaining power will be converted into mechanical form. Once the motor starts rotating, the rotational losses will start taking place, that will include the windage loss and the rotational loss, and the difference P converted minus V rotational will available at the rotor shaft as the output. So let's discuss a problem. We have a 1/3 horsepower single phase induction motor that has an input voltage of 110 volts. The supply frequency is 60, the number of poles are 6. The slip, which is the forward slip, is 5%, and the rotational losses are 51%. 51 watts. The motor impedances are also given: R1, X1, R2, X2, XM, and these values are referred to the stator side. The rotor side impedances are referred to the stator side. We have to find the speed, the stator current, the stator power factor, the input power, the air gap power, converted power, induced torque, output power, and efficiency. So first of all, let's calculate ZF and ZB, the forward impedance and the backward impedance. With this relation NS 120F by T, we can calculate the synchronous speed, the field speed. We can calculate the rotor speed 1 minus SF into NS. The motor is rotating at a speed of 1140 RPM. Once it is rotated by some external beams, we can calculate the stator current. I1 is V by ZT. The total impedance, it is obtained in this way. We will just see this equivalent circuit: R1 plus JX1 plus 0.5 RF plus 0.5 into JXF plus 0.5 RB plus 0.5 into JXB. So you can see that the same equation has been, the same equivalent circuit has been used to calculate the total impedance ZT. We can calculate the current I1. So the current is 4.4 amperes. The stator power factor can be obtained with the help of this angle. Cos of this angle, I think there is some typing mistake. This is 48.26. The same is used to calculate this cos of phi. However, the in writing there has been a mistake here. It is minus, it is minus 48.26 degrees. So P in the input power can be calculated as VI cos of phi. VI cos of phi. 325 watts is the input power. The part E is to calculate the air gap power. I think here the air gap power means the net air gap power. We can first of all calculate the forward air gap power in this way. I1 square 0.5 RF. The backward air gap power. Then we can calculate the net air gap power. It is 265 watts. The part F deals with the converted power. We are using one of the relations we have discussed, 1 minus SF into net PAG. This is net PAG. So we can calculate that it is 252 watts approximately. Then the induced torque can be calculated as P converted divided by omega R, or alternately we can use this relation, net PAG divided by omega S. Both of these relations will give us the same answer, 2.11 Newton meters. We can calculate the output power. It is P converted minus P rotational, 201 watts approximately. P out, the output torque is P out by omega R. Similarly, we can calculate the efficiency, which is approximately 62%. So, as a check of power bookkeeping, let's compute the losses. The stator copper loss is I1 square R1. The rotor copper loss is calculated in this fashion, 43 watts. The rotational losses are given 51 watts. The total loss is, can be calculated by adding these losses: stator copper loss, rotor copper loss, rotational loss. 124 watts approximately. So P in minus P loss will give us the output power, and we can see that it is still same, 201 watts. So our answer can be verified with the help of this alternate calculation scheme. Alternately, the power stages can also be calculated in this way. The input power that has already been calculated, 325 watts. The stator copper loss calculated above, 30 watts. The air gap power can be calculated, the total air gap power, that is crossing the air gap and is entering the rotor. It is P in minus P stator. The stator copper loss, it is 295 watts. This is the total air gap power, including the forward air gap power plus the backward air gap power. 295 watts are crossing the air gap and are entering into the rotor circuit. This air gap power is responsible for current flow in the rotor and is responsible for the power loss taking place in the rotor due to the current flow, that is the rotor copper loss, that is 43 watts. So we can calculate the converted power. Converted power is air gap power minus the rotor copper loss, it is 252 watts, minus the rotational power, it is give us the rotational loss, sorry, it will give us the output power. Again, the answers are same. So the alternate schemes can be used to calculate the output power or to calculate the power distribution in the single phase induction motor. Now, the single phase induction motor, as we have seen here, is not a self-starting motor. It requires some external force to be applied by some means to start the motor. Otherwise, if we just switch on the power supply, the motor will not rotate. The motor will remain stationary. How can we make the motor self-starting? How can we make a single phase induction motor to self-start by just switching on the supply? So there are alternate schemes that are used to make a single phase motor self-starting. One of the techniques is to use a split phase windings. The other is to use tester type windings. The other one will be the shaded stator poles. So we will limit ourselves to first two of the types that can be used to start the make a single phase motor self-starting motor. What is a split phase winding? A split phase motor is a single phase induction motor with two stator windings. One is the main stator winding as shown here, The other one is an auxiliary stator winding, and we can see from the, or we can recall the discussion about the two-phase armature construction. In the very first lecture of the AC machines, we discussed the stator construction for a two-phase machine. Just recall that, where we discussed that both the winding for both the phases will be at an angle of 90 electrical degrees to each other. So here the same concept has been used. The two windings are set at an angle of 90 degrees to each other. The auxiliary winding is connected in the circuit with the help of a centrifugal switch. It can be shown here. This is a centrifugal switch. So a centrifugal switch will operate on the principle of centrifugal force. When the speed of the motor will increase, or the motor will attain speed up to a certain extent, the centrifugal force will make the switch open. Otherwise, below that speed, the switch will remain closed. So the auxiliary winding is connected with the circuit with the help of a centrifugal switch that will operate on the basis of speed. If the speed of the motor becomes larger than 70 to 75% of the rated speed, the centrifugal switch will operate and it will disconnect the auxiliary winding from the circuit. Below that speed, the centrifugal switch will remain closed and the auxiliary winding will remain connected in the circuit. The auxiliary winding is designed in such a way that a very thin wire is used for this winding. It means that it will have much higher resistance to reactance. The reactance will be smaller as compared to resistance. The auxiliary winding is designed in such a way that the resistance dominates in this winding. So we can see that normal in the starting condition, this switch is closed. The switch is closed. We can see in this fashion, the switch is closed and the current will flow in the main winding as well as in the auxiliary winding. Since the winding has been designed in such a fashion that the resistance dominates to the reactance, it means that the current drawn by the auxiliary winding will lag the voltage by a small angle. And since the resistance is larger, it is made of thin wire, the current IA is smaller in magnitude as compared to current IM. The magnetizing, the main winding is designed in such a way that here we want to limit the losses in the motor when the motor is in under operating in normal operating condition. When the motor is running under normal operating condition, we want to minimize the stator copper losses. So if we want to minimize the stator copper losses under normal running condition, it means that Rm will be much smaller as compared to Xm. So it means that in the main winding, the reactance effect, the reactive effect will dominate as compared to the resistance. So the current Im will lag behind the voltage by a large angle. Since our resistance of the main winding is designed to have a small value to keep the stator copper losses to minimum under normal running conditions, because the main winding is connected under normal running conditions, the auxiliary winding will be disconnected. It is just included in the circuit to make the motor self-start, to start the motor. Resistance is dominating, IA is lagging the voltage by a small angle, the reactance is dominating, IM is lagging behind the voltage, applied voltage by a large angle. So we can see that we have two currents that are lagging by some angle. Definitely this current IA will produce a flux phi A, this current IM will produce a flux phi M, and both of the fluxes have some angle difference between them. You can recall the two-phase stator construction and you can see that in a in a two-phase supply, we may have a symmetrical or a balanced two-phase supply with IA, IM equal in magnitude and they have an angle of 90 degrees between them, or we may have an unbalanced two-phase supply where we may have different magnitudes of the two currents, or the two currents may be at an angle of other than 90 degrees to each other. So you can see that actually with the help of this auxiliary winding, we have splitted a single phase current into an unbalanced two-phase supply, IA and IM, that are at an angle of that are at some angle to each other, that are making some angle to each other. So this two-phase supply, when provided to this stator, it will produce a revolving magnetic field. This revolving magnetic field is shown here. The current is shown here. The current IA, the current IM, both are at an angle to each other. This is resembling to a two-phase supply. It will produce a revolving field. The direction of the revolving field now can be calculated with the help of thumb rule that we have already discussed in the first chapter of the AC machines. The thumb rule learned was the magnetic field always revolves in a direction from the conductor carrying leading current towards the conductor that is carrying lagging current. That is, in this case, from conductor A towards conductor M. It means that the field will be revolving in the counterclockwise direction. The current is entering in conductor A, leaving through conductor A prime. The current is entering to conductor M, leaving through M prime. So the field will revolve in this direction from A to M, from conductor carrying leading current towards the conductor carrying lagging current. So we will have a revolving field which is revolving in counterclockwise direction. So once the revolving field is produced, the motor will just behave like a two-phase induction motor, just like a motor which has provided with polyphase supply. The motor will become a self-starting motor. As we switch on this supply, the motor will start rotating in this particular direction. Once the motor has attained 70 to 75% of the rated speed, the centrifugal switch will operate and it will disconnect the auxiliary winding from the main circuit. Now the motor will keep on rotating with the help of only the main winding. So the torque speed characteristics have been shown here. You can see that this line is showing the torque speed characteristics for only the main winding alone, as we have already discussed. Now, once the starting winding or the auxiliary winding has been added, we will have some starting torque that will be produced, and this curve is showing the condition when the motor is running with both the windings, the starting winding or the auxiliary winding plus the main winding. At this stage, at approximately 70 to 75% of the rated speed, the centrifugal switch will operate. The centrifugal force will become so large that it will make the centrifugal switch to operate. So it will disconnect the auxiliary winding from the main circuit. So now the motor will start rotating with only main winding alone, and this curve will start, and this curve will now be considered. This curve will now be considered up from this point onwards, from this stage onwards. So this will be the effectively the torque speed curve followed by the motor. Up to this point, the switch will operate. The torque produced will now be decreased because now the motor is running with the help of a single winding. So this curve will be followed, as which is shown by more dark black line. Shown here. The switch is shown here. Now, if we want to reverse the speed or we want to change the direction of rotation of this split phase induction motor, what we can do? Just you have to interchange the connections of the auxiliary winding. Previously, the current was entering to A, leaving through A prime. Now the current will enter to A prime and it will leave through A. The remaining direction remains same. Current is entering in conductor M, leaving through M prime. However, the current flow direction in the auxiliary winding has been reversed. You can see that following the thumb rule, the current, the magnetic field will revolve in a direction from conductor carrying leading current towards the conductor carrying lagging current. So the field will now rotate in this direction, that is the clockwise direction. And the instantaneous direction of the field, of the revolving field, can be determined with the help of the application of right hand rule. These two conductors will behave as a single big conductor carrying current into the board. These two conductors are behaving as a single big conductor carrying current out of the board. So the curling of the fingers will show the direction of current flow into the paper, out of the paper, and the thumb will point in this particular direction or the instantaneous direction of the revolving field. The commercial name of the centrifugal switch is known as is clutch. Commercially, the centrifugal switch is known as clutch. So this is an alternate name for the centrifugal switch. So these motors find application where the moderate starting torque is required with low starting current, and the applications include fans, blowers and centrifugal pumps. These motors are available in fractional horsepower ratings. Typical range is 50 watts to 500 watts and are quite inexpensive. The reversal of direction of rotation has been discussed already. So let's move forward to the capacitor start induction motor. So in this case, just observe the first motor, the split phase motor. We have included a capacitor in the auxiliary winding circuit. The main difference between this figure and this figure is that of a capacitor. Here we have provided a capacitor in the auxiliary winding. We have provided an auxiliary winding in the stator, and also we have connected a capacitor in series with the auxiliary winding. Centrifugal switch is again there. Now the capacitor will change the current behavior behavior of the current IA. Again, IM is lagging behind V by a large angle because RM is smaller to reduce the stator copper loss in normal running condition. Now see the current IA. With the help of capacitor, we can adjust the angle between the current IA and the current IM, the auxiliary winding current and the main winding current. We can even attain an angle of 90 degrees between these two by suitable selection of the capacitor size, as we will discuss in the uh, afterwards, as we will discuss afterwards, that how can we design a proper capacitor size, how can we select a proper capacitor size to attain any desired angle between the auxiliary winding current and the main winding current. So since a capacitor is provided in the auxiliary winding, the behavior of this winding will change. We can see that here the current is leading the voltage by some angle because of this capacitance which is included in the auxiliary winding circuit. So the angle between IM and IA has increased. If the angle between IA and IM is equal to 90, and let's assume that both IA and IM are equal in magnitude, we can obtain a balanced two-phase supply. What is a balanced two-phase supply? Two currents equal in magnitude at an angle of 90 degrees to each other. So by a suitable selection of capacitor size, we can split a single phase current I into a balanced two-phase supply with IA, IM equal in magnitude, and they are at an angle of 90 degrees to each other. So in this technique, again the motor will start as a two-phase motor. Just recall that a polyphase supply produces a revolving field. The motor is a self-starting motor. The difference between this motor and the split phase motor is that it will produce large starting torque. The starting torque produced by this motor will be larger than the previous one. The reason is that, just see here, just see this torque equation. K is IR sine of delta. Previously, IA, we have two currents, I, or we can write it ISIR, or we can write it as I1, I2, I main, I auxiliary, sine of delta between these two, sine of the delta between the two currents. So if we just recall the split phase motor case, the auxiliary winding current was small in magnitude and the angle delta between the two currents was quite small. The angle delta between the two currents was quite small, as we can see here. IA is smaller in magnitude as compared to IM, and the angle delta between these two, the phase displacement between IA auxiliary and IM is quite small. So it means that the torque will have small magnitude, small starting torque that is available. If we manage to increase the current magnitude of the auxiliary winding current, and we manage to obtain an angle of 90 degrees, that is delta becomes 90, the torque will be increased. So we can produce large starting torque with the help of this technique by including a capacitor in the auxiliary winding circuit. So these motors are used where high starting torque is required, and the typical applications are compressors, pumps, air conditioners, and the load where are such types of loads where the motor must start under load, where the motor must be started under loaded condition. So the torque speed characteristics for a capacitor start motor are shown here. You can see that as compared to the previous case, the torque has been increased. The starting torque has been increased. Here the torque has been increased. At this stage, both the main and auxiliary winding are in the circuit, are operational. When the motor will attain 70 to 75% of the state, the centrifugal switch will operate and it will disconnect the auxiliary winding from the circuit. Now the motor will operate with only main winding from this stage onwards. Previously, it is operating with both the windings. At this stage, the switch will operate and the motor will now operate with only main winding. We can have another variation of the capacitor type motors. Just recall the function of the capacitor. We can summarize the functions of the capacitor. Due to this capacitor, the motor becomes self-starting because it is used to produce the balanced two-phase supply, which will produce a revolving magnetic field. The capacitor also helps to improve the starting torque, as we have just seen that the auxiliary winding current magnitude has increased. We can also adjust the angle delta between the two currents, so the starting torque will improve, and the inclusion of the capacitor in the equivalent circuit at start will also improve the starting power factor of the motor. We can recall the discussion about the synchronous motor, where we discussed that a synchronous motor behaves as a capacitor, and what a capacitor do? A capacitor improves the power factor. So the capacitor will also improve the power factor of the motor at start. The other type of capacitor motor is a permanent capacitor motor or a permanent split capacitor. The starting capacitor is so useful, as we have summarized the advantages of the inclusion of capacitor in the auxiliary winding circuit, that sometimes it is left permanently in the motor circuit. If the capacitor value is correctly selected, such a motor will behave just like a two-phase induction motor throughout its operation, and it is known as a permanent split capacitor motor or as a capacitor start and run motor. The permanent capacitor motors are simpler than capacitor start motors because the centrifugal switch is not required. They have a higher power factor and smoother torque in normal running condition as compared to ordinary single phase induction motors that operate with only main winding after the centrifugal switch has operated. However, these motors have comparatively lower starting torque as compared to the capacitor start motors because the capacitor size now should be selected in such a way that the auxiliary winding can be energized throughout the motor operation, can be kept left energized under normal loading conditions. If we use a very large capacitor size here for the permanent capacitor motor, the large capacitor will draw large current, the auxiliary winding will become overheat, and it will be damaged if it is kept connected in the circuit during normal operating conditions. So in order to provide safety to the auxiliary winding, now the capacitor should be properly selected in such a way that it should not draw such a heavy current that cause overheating of the auxiliary winding and damaging of the auxiliary winding. Capacitor start, capacitor run motors. So in order to improve the starting torque and in order to gain the advantages of the permanent capacitor motor, we have another variation of capacitor type motors where we have two capacitors. At start, the centrifugal switch is closed. We have two capacitors in the motor. One is known as the starting capacitor, the other one is known as the running capacitor, or the capacitor which is permanently connected in the motor. So the motor will be started with two capacitors in the auxiliary winding circuit. It will draw a very large current at start, so it will produce a very large starting torque because of the large magnitude of the current and because of the large angle which will be obtained between the auxiliary winding current and the main winding current. Once the motor has attained up to 75% of the rated speed, the switch will operate and it will disconnect the starting capacitor from the motor circuit. Now the motor will keep on operating as a two-phase motor with only the running capacitor in the motor. You can see that the running capacitor is connected permanently. There is no centrifugal switch in its circuit. The starting capacitor has been disconnected, so the motor will keep following this torque speed characteristics as we can see here for a permanent capacitor motor. This is the circuit for a permanent capacitor motor, no centrifugal switch. The starting torque is quite small because of this limitation of the capacitor size. If we use a large capacitor size to improve the torque, it will damage the auxiliary winding in normal running condition. So this is the torque speed characteristic for a motor with permanent running capacitor. Here the same curve has been redesigned with the help of another capacitor that is connected just at start to improve the starting torque. Then the motor will switch to this curve when the centrifugal switch will operate. With the help of the capacitors, we can make the motor self-start and we can obtain the advantages of like improving power factor, improving the starting torque and the reduction in the starting. So let's move on to some numerical problems that are related to the split phase and capacitor type induction motors. The first one deals with a split phase induction motor. The data is given. We have a 120 volt 60 hertz split phase induction motor. The main winding and auxiliary winding parameters are given. You have to calculate the motor starting current in each winding, that is I main and I auxiliary have to be calculated. You have to calculate the phase displacement between the two currents, that is angle delta is to be calculated. You have to calculate the starting torque of the machine, and if the impedance of the auxiliary winding is changed, we have redesigned the auxiliary winding, or just assume that approximately 5 ohms have been externally connected with the auxiliary winding. This auxiliary winding we connected some external resistance equal to approximately 5 ohms, or we changed the auxiliary winding parameters in such a way that the auxiliary winding parameters are now shown as R auxiliary, just an addition of 5 ohms. The reactance of the auxiliary winding is same, 8.4. You have to determine the phase displacement between the two currents now. Again, the angle delta is to be calculated. Now, for the new conditions, you have to calculate the starting torque that is developed by the machine and the percentage change in the starting torque as compared to the old starting torque. So let's first of all draw the equivalent circuit of the machine, the stator side equivalent circuit. The main winding and the auxiliary winding are connected in parallel to each other. The voltage, applied voltage, is appearing across both the windings. It is used to calculate the main winding current. It is used to calculate the auxiliary winding current. You can see here. Now we can plot these angles. The voltage applied is taken as the reference at 0 degrees. The current I main is lagging behind the voltage by 60 degrees. Lagging behind, it means that we will draw it below the line in the clockwise direction. The other one, the auxiliary winding, is lagging behind the voltage by 42.6 degrees. Now the angle delta can be calculated as the difference of these two. It is 17.7 degrees, as you can see here. Mod of the angle 60.3 minus 42.6 is 17.7 degrees, or we can use this phasor diagram to calculate this angle delta. 60 degrees lagging behind the voltage, main auxiliary winding current, lagging behind the applied voltage by 42.6 degrees. The difference of these two is 17.7 degrees. So we can calculate the starting torque using the relation that we have discussed. This relation is used to calculate the starting torque, the main winding current, the auxiliary winding current, the angle between these two. K is some constant, so we can write the starting torque in terms of some constant, 87.45 into some constant Newton meters. Now, for the new conditions, when the auxiliary winding impedance has been, auxiliary winding resistance has actually been changed, the new auxiliary winding current here, this angle can be used to calculate the new value of angle delta. The new value of angle delta is 30.0 degrees approximately. The new value of the starting torque can be calculated as the constant, the main winding current, which will remain same, 29.8 amperes. The new value of the auxiliary winding current magnitude, it is 7.2 amperes, and the new value of angle delta, that is sine of 30 degrees. Sine of 30 degrees, we can obtain the new value of the starting torque, which is 107.4 into some constant Newton meters. Now we can calculate the increase in the starting torque as a percentage of the original torque. You can see that by increasing the resistance of the auxiliary winding, the starting torque produced by the motor has improved because of the improvement in the angle delta. Also, you can see that the auxiliary winding, the starting current drawn by the motor has decreased. It is 7.2. Previously, it was 9.6. However, since the angle delta has been improved because of the dominating effect of the auxiliary winding resistance, the starting torque of the motor, the starting torque dealt by the motor has been improved. Using the same data of the previous motor, now let's discuss a capacitor type induction motor, capacitor type single phase induction motor. We have to calculate the capacitance that is required to be placed in series with the auxiliary winding to obtain an angle of 90 degrees between the current in the main winding and the auxiliary winding current at start. And we have to calculate the starting torque dealt by this machine. Just recall the main winding parameters, the auxiliary winding parameters. We can convert these into this form: the magnitude, the angle, magnitude, the angle. So basically, what is this? This is the phi impedance auxiliary, the auxiliary winding impedance angle. It is 42.6 degrees. Using these values and using the voltage value from the previous example, we have already calculated the main winding currents and the auxiliary winding current. These are the same. These are the same values. Now, in that motor, in the motor of the previous example, we now want to place a capacitor such that the angle between the two currents becomes equal to 90. So let's redraw the phasor diagram. The applied voltage is taken as the reference. With respect to the reference, I main is lagging behind by an angle of 60.3 degrees. Now, since the conditions have been changed, we have added a capacitor. The angle between these two, the angle between the current of the main winding, the angle between the current of the auxiliary winding is equal to 90. We can calculate the angle phi I auxiliary nu. Auxiliary winding current nu angle by which it is lagging or leading the voltage V. So 90, which is angle delta now, delta is now 90. 90 minus 60.3 mod of this angle, 60.3 will be subtracted from 90. We can obtain this angle. So phi I auxiliary nu, this angle, which will be calculated, the new value of the auxiliary winding current, which will be calculated afterwards. So phi I auxiliary nu will now 29.7 degrees. That is this angle. This angle between the voltage and this auxiliary winding new current for the new conditions is 29.7 degrees. Just adding 29.7 with 60.3, we can obtain 90. That is 90 between the two currents I main and I auxiliary. So after the installation of capacitor, the equivalent circuit will look like of this form: the main winding circuit, the auxiliary winding circuit. You can see that now a capacitor has been added here, which is shown by the negative impedance JXC as compared to the positive impedance JXL. Applying Ohm's law to the auxiliary winding, we can calculate the new parameter of the auxiliary winding impedance. Applied voltage divided by the new current after the installation of capacitor the magnitude is still not known. However, the angle has been calculated here, 29.7 degrees. It is leading by this angle with the applied voltage. The angle is positive. So we can use this equation and see that V by I mod will give us the magnitude of the impedance along with the angle. You can see that the sign with the impedance angle is negative. Phi I auxiliary nu is positive because it is the angle with the current. This angle when come upward, 0 minus 29.7 degrees, it will give us minus 29.7 degrees. So this is phi impedance auxiliary nu. The magnitude is still not known. The angle for the impedance has been calculated. We can use this information to calculate the capacitor size. We can write the equation for the impedance in this form: R plus jXL minus jXC, or we can write alternately in this form: resistance, reactance. We can draw the impedance triangle. Now, as the angle phi z auxiliary nu is negative, so it means that the impedance triangle will be drawn in this fashion: R auxiliary, the auxiliary winding resistance, jXL minus jXC, the angle will be negative, so the impedance triangle is drawn in such a fashion. So the auxiliary winding impedance is given as the phasor sum of these two. So from this impedance triangle, tan of this angle is equal to perpendicular by base. This is perpendicular, XL minus XC. This is base or auxiliary. The angle is negative, minus 29.7 degrees. Tan of the angle minus 0.57, and we can solve this equation in this form to obtain XC. It is 13.62 ohms. XC is 1 by 2 pi FC, so we can calculate the capacitance. If we connect a capacitor equal to 194.7 microfarads, we will obtain the angle of 90 degrees, an angle of 90 degrees between auxiliary winding and the main winding current, or in other words, we can say that this capacitor of 194.7 microfarads will place the auxiliary winding current in quadrature with the main winding current. Now, with this information, we can calculate the new magnitude of the auxiliary winding current, or I auxiliary nu. Applied voltage, the impedance or the resistance of the auxiliary winding, as you can see here, 9.15 plus 8.4 plus minus 13.62 J, because it will come with minus sign. If this is positive, this will be negative. The capacitive reactance will be subtracted from the inductive reactance. It will decrease the overall reactance of the branch. So following this, we can get the current magnitude. The angle is already known to us. Starting torque can be calculated using the magnitude of the main winding current, the auxiliary winding current, the angle delta, that is 90 degrees. So the torque is 339 into some constant Newton meters. Now just see that how much the torque, starting torque produced by the motor has improved as compared to the original motor, which was just a split phase motor. The increase in torque is approximately 287% as compared to the original split phase motor. If we compare this torque with the second case, where the torque was improved by increasing the resistance of the auxiliary winding, we can see that the torque has been improved by 216%.